There is a table in front of you. Perhaps you cannot see it right now. Perhaps the room is dark and your eyes are closed, and the world has narrowed to the soft weight of a blanket and the sound of your own breathing. But somewhere near you, there is a surface, a table, a floor, a wall, something solid and ordinary and unmoving, something that has always been exactly what it appears to be, something that you have never had any reason to question. This is where we begin, not with galaxies or black holes, or the vast empty distances between stars. We begin here, in the ordinary world, with the things that seem most certain. A table, a hand, a breath of air. We begin with the familiar, because what we are about to discover is that the familiar is not what it seems. Beneath the surface of everything you have ever touched or seen or held, there is another world. A world so strange, so unlike the one we inhabit, that physicists who have spent their entire lives studying it still find themselves unable to fully believe what they have found. This is the quantum world. It has always been there. It is there right now, beneath your fingertips, inside the air filling your lungs, inside the neurons firing gently in your brain as you drift towards sleep. It is the foundation of everything, the invisible machinery running beneath the surface of all that exists. And it operates according to rules so different from the ones we know that to describe it accurately is, in some sense, to describe a reality that no human being has ever directly experienced. We will go there slowly. There is no hurry. The quantum world has existed for as long as the universe itself, and it will exist long after everything we know has changed. It will wait for us, so we move carefully, step by step, beginning at the surface and descending, layer by layer, into the deepest structure of things. Begin with that table. Run your hand across its surface, or imagine doing so. You feel something solid, something that resists your touch, something that has edges and weight and a particular texture, smooth or rough, warm or cool. This is what we mean when we say something is real. It is there. It pushes back. It occupies space. It has a definite location in the world. For most of human history, this was the whole story. The world was made of stuff. Solid, tangible, reliable stuff. Rocks and wood and water and air. Things you could touch and measure and trust. The ancient Greeks argued about what this stuff was made of. Some said fire, some said water, some said all four elements together. But they agreed on the essential point. Reality was material. It was out there, independent of us, behaving according to consistent rules, available to be studied and understood. This picture held for a long time. It was refined and improved over centuries. By the 17th century, scientists had developed a sophisticated version of it. Matter was made of particles, tiny, hard, indivisible objects moving through empty space according to fixed mathematical laws. If you knew the position and speed of every particle in the universe at a given moment, you could in principle calculate the entire future of everything. The universe was a machine, a very large, very complex machine, but a machine nonetheless. Predictable, deterministic, knowable. It was a deeply satisfying picture. It explained an enormous amount. It allowed engineers to build bridges and astronomers to calculate the orbits of planets and chemists to understand why substances combined the way they did. For a long time, it seemed that the work of physics was essentially complete. The details remained to be filled in, but the broad outlines were settled. And then, around the turn of the 20th century, things began to go wrong. Not dramatically, not all at once. The problems appeared quietly, at the edges of the picture, in experiments that seemed at first like minor puzzles rather than fundamental crises. A strange pattern in the light emitted by hot objects. An odd behavior of electrons when struck by light. small anomalies in the way matter absorbed and released energy. Physicists began to notice that the universe was not quite behaving the way it should. The machine had a flaw. To understand what the flaw was, we need to go smaller. The table you are imagining is made of wood or metal or glass, some material with its own particular properties. But whatever it is made of atoms. This was understood with reasonable confidence by the late 19th century. Atoms were the smallest units of matter, tiny indivisible particles that combined in different arrangements to form all the different substances in the world. A molecule of water was 2 hydrogen atoms bonded to 1 oxygen atom. A piece of iron was a lattice of iron atoms packed tightly together. Everything, ultimately, was atoms. The word atom comes from the Greek atomos, meaning indivisible. The Greeks who coined the term imagined atoms as the smallest possible pieces of matter, objects that could not be cut or broken or divided further. This was a reasonable hypothesis, and for a long time it seemed to be correct. Atoms were so small that they could not be seen directly, and chemists worked with them indirectly through the patterns they left in chemical reactions and the ratios in which substances combined. But by the end of the 19th century, the evidence for their existence was overwhelming. Then, in 1897, a British physicist named J.J. Thomson made a discovery that changed everything. Thomson was studying something called cathode rays, streams of particles that flowed between electrodes in a glass vacuum tube when an electric current was applied. He found that these particles were identical regardless of what material the electrodes were made of. They were far smaller than any atom. They carried a negative electric charge, and they appeared to be present in all matter. Thomson had discovered the electron. This was the first indication that atoms were not in fact indivisible. They contained something smaller. And if they contained electrons, they must also contain something with a positive charge to balance it. The atom as a whole is electrically neutral. Thomson proposed a model in which the atom was a sphere of positive charge with electrons embedded in it, like raisins in a pudding. This model did not last long. In 1909, a physicist named Ernest Rutherford, working in Manchester, conducted an experiment that would overturn it entirely. Rutherford's experiment was elegant in its simplicity. He took a thin sheet of gold foil, just a few atoms thick, and fired a stream of positively charged particles at it. These particles, called alpha particles, were known to be relatively massive and energetic. The expectation based on Thomson's model was that they would pass through the gold foil more or less in a straight line, deflected only slightly by the diffuse positive charge of the gold atoms. What actually happened was very different. Most of the alpha particles did pass straight through the foil, which was expected. But a small number, perhaps 1 in 8,000, bounced back at large angles. Some bounced almost directly backward, as if they had struck something very hard and very dense. Rutherford later described his reaction. It was as if you had fired artillery shells at tissue paper and they had bounced back at you. The explanation he developed was this: the atom was not a diffuse sphere of positive charge. Instead, almost all of the atom's mass and all of its positive charge were concentrated in an incredibly tiny central region, a nucleus, surrounded by a vast empty space through which electrons moved. The atom was not solid at all. It was almost entirely empty. Think about what this means for that table. The table appears solid. When you press your hand against it, it does not yield. It has a surface that you can feel and measure and trust. And yet the atoms that make up the table are almost entirely empty space. The nucleus of an atom is roughly 100,000 times smaller than the atom itself. If an atom was scaled up to the size of a cathedral, the nucleus would be about the size of a grain of sand in the center of the nave. The electrons would be tiny specks moving somewhere near the walls. The rest would be nothing. Empty space. And the same is true of your hand. The atoms in your hand and the atoms in the table are both almost entirely empty. When you press your hand against the table and feel resistance, what you are feeling is not solid matter meeting solid matter. What you are feeling is electromagnetic force, the repulsion between the electrons in your hand and the electrons in the table. The sensation of solidity is, at the atomic level, a force field, a kind of invisible pressure between regions of mostly empty space. This is one of the first strange things about the world at the atomic scale. The solidity of things, the quality that seems most fundamental to our experience of reality, is, in a deeper sense, an illusion. Not an illusion in the sense that it is not real, because the force you feel is perfectly real, but an illusion in the sense that it is not what it appears to be. The table is not solid in the way you imagine it to be. It is a collection of nearly empty atoms held together and apart by invisible forces, presenting a surface to your hand that feels unyielding, but is, at the level of its actual constituents, almost entirely air. The deeper you look, the stranger things become. The Rutherford model of the atom, a tiny nucleus surrounded by electrons moving through empty space, raised an immediate problem. According to the physics of the time, an electron moving in a circle around a nucleus should continuously radiate energy. As it lost energy, it should spiral inward, getting closer and closer to the nucleus until it crashed into it. This process should happen almost instantaneously. Within a fraction of a second of the atom's formation, every electron in every atom in the universe should have spiraled into its nucleus. Matter itself should be unstable. Atoms should not be able to exist. And yet atoms clearly did exist. The universe was full of them. They were stable. Electrons did not spiral into nuclei. Something was wrong with the physics. In 1913, a young Danish physicist named Niels Bohr proposed a solution. He suggested that electrons did not in fact move in arbitrary orbits around the nucleus. Instead, they were constrained to move only in certain specific orbits. Fixed energy levels, like steps on a staircase. An electron could occupy one step or another, but it could not exist between steps. And while it remained in its orbit, it did not radiate energy. It simply moved, stably, without losing anything. When an electron moved from a higher energy level to a lower one, it released a specific amount of energy, a packet of light with a precise wavelength. When it absorbed energy, it jumped from a lower level to a higher one. These jumps between levels were instantaneous and discrete. The electron did not travel smoothly from one orbit to another. It simply disappeared from one and appeared in the other. This was strange, but it worked. Bohr's model accurately predicted the specific wavelengths of light emitted by hydrogen atoms, which had been measured precisely in laboratories and had never been satisfactorily explained. Something about his picture, the fixed levels, the discrete jumps, was capturing something real about the behavior of electrons. But why? Why should electrons be confined to specific orbits? Why should they jump between levels rather than moving smoothly? Bohr had no answer. His model was a description of what happened, not an explanation of why. To find the why, physicists would have to go deeper still. The next step came from an unexpected direction. In 1905, 8 years before Bohr's model of the atom, Albert Einstein had published a paper explaining a phenomenon called the photoelectric effect. The photoelectric effect was one of those small anomalies that had been troubling physicists for years. When light shone on certain metals, electrons were ejected from the metal's surface. This made sense. Light carries energy, and that energy could knock electrons loose. But the details were puzzling. The energy of the ejected electrons did not depend on the brightness of the light, as expected. It depended only on the color, the frequency of the light. Dim blue light ejected electrons with more energy than bright red light, and below a certain frequency, no electrons were ejected at all, regardless of how bright the light was. This made no sense if light was a wave, a smooth, continuous oscillation spreading through space. A wave's energy should depend on its amplitude, its brightness, not its frequency. But Einstein proposed something different. He suggested that light was not a continuous wave, but was made of discrete packets of energy. Quanta, he called them, later renamed photons. Each photon carried an amount of energy determined by its frequency. A blue photon carried more energy than a red photon, and an electron could only be ejected if it was struck by a photon with enough energy to free it, which depended on frequency, not brightness. This explained the photoelectric effect perfectly. But it raised a profound question. Light had been conclusively shown to be a wave. The evidence was overwhelming. Light produced interference patterns, it diffracted around obstacles, it behaved in every measurable way, exactly as a wave should behave. And now Einstein was saying it was also made of particles. How could something be both a wave and a particle? These were not just different things, they were opposite things. A wave was a disturbance spreading through a medium, spread out over space. A particle was a discrete object occupying a definite location. Physics had no framework for something that was both. The puzzle deepened in the 1920s when a French physicist named Louis de Broglie made a bold suggestion. If light, previously thought to be a wave, could behave like a particle, perhaps the reverse was also true. Perhaps particles, previously thought to be discrete objects, could also behave like waves. De Broglie proposed that every particle of matter had an associated wavelength, determined by its momentum. The faster and more massive a particle, the shorter its wavelength. For large objects, a thrown ball, a speeding car, the wavelength would be so incredibly small as to be completely undetectable. But for very small, very light particles like electrons, the wavelength might be large enough to produce measurable effects. This was not immediately taken seriously. It seemed too strange, too abstract. But within a few years, experiments confirmed it. Electrons fired through a crystal lattice produced diffraction patterns, the characteristic signature of waves interfering with each other. Electrons were behaving like waves. But electrons were also behaving like particles. They arrived at detectors one at a time, producing individual discrete impacts, not a smooth continuous spread of energy. They had specific locations when you looked for them. So what were electrons? Waves or particles? The answer, which physicists arrived at through decades of careful experiment and theoretical work, was deeply uncomfortable. Both. And neither. The electron was something for which human language and human intuition had no good word, because it was something that had never existed in the world humans had evolved to navigate. It was a quantum object, and quantum objects obeyed their own rules. The experiment that made this most vivid, that brought the strangeness of quantum mechanics into the sharpest possible focus, was simple enough to describe, though its implications are still being debated a century later. It is called the double-slit experiment. Imagine a barrier with two narrow slits cut into it side by side. Behind the barrier is a screen that can detect whatever strikes it. Now imagine firing electrons at the barrier, one at a time, and watching where they land on the screen. If electrons were ordinary particles, like tiny ball bearings, you would expect them to pass through one slit or the other and land in two bands on the screen, one behind each slit. This is what would happen if you fired bullets through the same setup. But this is not what happens. When many electrons have been fired and their landing positions recorded, the pattern on the screen is not two bands. It is an interference pattern, a series of alternating light and dark stripes, exactly like the pattern you would see if you sent waves through the two slits. The waves passing through the two openings would overlap and interfere with each other, reinforcing in some places and cancelling in others, producing exactly this kind of striped pattern. But the electrons are arriving one at a time. Each electron produces a single discrete impact on the screen. There is no continuous wave. And yet, over time, the individual impacts accumulate into an interference pattern. Each single electron passing through the apparatus alone seems to be interfering with itself, as if it passes through both slits simultaneously, like a wave, and interferes with its own two parts, and yet arrives as a single particle in a single location. This is impossible by any ordinary logic, but it gets stranger. Suppose you add a detector to the apparatus, a device that will tell you which slit each electron passes through. Now you can know which path each electron took. And when you do this, when you add the measurement, the interference pattern disappears. The electrons begin landing in two bands, one behind each slit, exactly as you would expect from particles. The act of measuring which slit the electron passes through changes the outcome of the experiment. Not because the detector disturbs the electron physically, though that is sometimes offered as an explanation. The effect persists even when the measurement is designed to be as gentle as possible. Something more fundamental is happening. The electron, when unobserved, exists in a superposition of states, passing through both slits, following all possible paths simultaneously. When it is observed, when a measurement is made, this superposition collapses. The electron is forced to commit to a single definite path. Reality, at the quantum level, is not fixed until it is looked at. This idea, superposition, is the heart of quantum mechanics, and it is worth sitting with for a moment before moving on. In ordinary life, things have definite properties. A coin is either heads or tails. A cat is either in one room or another. A switch is either on or off. The property exists independently of whether you look at it. Looking at the coin doesn't determine whether it is heads or tails. It simply reveals what was already the case. At the quantum level, this is not true. Before a quantum particle is measured, it does not have definite properties. An electron does not have a definite position. It exists as a wave of probability, a mathematical object called a wave function that describes not where the electron is, but the probability of finding it in various places if you were to look. The electron is, in some sense, everywhere and nowhere simultaneously. It is in a superposition of all the possible positions it might have. When you measure the electron, when you interact with it in a way that forces it to have a definite position, the wave function collapses. The electron becomes localized. It is found in a single place. But which place it is found in cannot be predicted with certainty, even in principle. The best you can do is calculate the probabilities. The electron might be here, or it might be there, and quantum mechanics can tell you the odds, but not the outcome. This was deeply troubling to many physicists, including Einstein, who spent the rest of his life arguing that quantum mechanics must be incomplete. God, he famously insisted, does not play dice with the universe. There must be hidden variables, additional information that, if known, would make the outcome predictable. The randomness must be a feature of our ignorance, not of reality itself. But experiments conducted decades later, testing specific predictions that Einstein himself helped develop, showed that Einstein was wrong. The randomness is not a product of ignorance, it is fundamental. At the quantum level, the universe genuinely does not determine outcomes in advance. Events happen with certain probabilities, and until they happen, they are genuinely undetermined. The universe plays dice. Niels Bohr, who spent more time thinking about what quantum mechanics meant than almost anyone else, had a response to the discomfort that these ideas produced. He suggested that asking what was really happening to an electron when no one was looking was the wrong kind of question. Quantum mechanics was not a description of reality as it was, independent of observation. It was a description of what could be measured and predicted about reality. The question of what the electron was doing between measurements was not a question science could or should try to answer. This view, called the Copenhagen interpretation, after the city where Bohr worked, became the dominant framework for most of the 20th century. It was pragmatically successful. It told physicists how to calculate, how to predict, how to build devices that depended on quantum effects. It did not tell them what was really going on, and Bohr suggested that this was fine. What is really going on was perhaps not a question with a meaningful answer. Other physicists found this unsatisfying. Hugh Everett, in the 1950s, proposed a different interpretation. He suggested that the wave function never actually collapsed. Instead, when a measurement was made and a quantum system seemed to choose between possibilities, the universe branched. Every possible outcome occurred in a different branch of reality. In one branch, the electron was here. In another, it was there. All possibilities were realized. Most physicists who have thought carefully about this view, the many worlds interpretation, find it mathematically consistent, even compelling. But it is strange in its own way. It implies that every quantum event produces an infinite proliferation of branching universes, each as real as our own. Neither interpretation is entirely satisfying. The debate about what quantum mechanics really means, about what is actually happening at the quantum level, about the relationship between the wave function and reality, continues today. A century after the theory was developed, physicists still do not agree on what it is telling us about the nature of the world. What they do agree on is this: the theory works. Its predictions are the most precisely confirmed in the history of science. It has never been wrong. And the world it describes is not the world we thought we lived in. Werner Heisenberg was 23 years old when he began the work that would lead to one of the most fundamental discoveries in the history of physics. It was 1925. Heisenberg was working in Göttingen, Germany, in the group of Max Born, one of the leading physicists of the era. He had been trying for months to develop a mathematical framework that could explain the behavior of electrons in atoms, why they occupied specific energy levels, why they jumped between levels in discrete steps, why the light they emitted had the specific wavelengths it did. The approach he took was radical. He decided to abandon the idea of describing the electron's position and trajectory, its path through space, and instead work only with quantities that could actually be measured. The position of an electron between measurements was not measurable. Its exact trajectory was not measurable. What was measurable were the wavelengths and intensities of the light it emitted. So he built his mathematics around those, and only those. The result was a mathematical structure of considerable strangeness and elegance that correctly predicted the behavior of electrons in ways that previous approaches had failed to achieve. But the mathematics contained something unexpected. When Heisenberg examined the properties of his framework, he found that certain pairs of quantities were linked in a peculiar way. Position and momentum, the two quantities that classical physics used to describe the state of a particle, were connected by a fundamental constraint. The more precisely you knew an electron's position, the less precisely you could know its momentum, and vice versa. The product of the uncertainties in these two quantities could never be less than a specific minimum value, determined by Planck's constant, the same fundamental constant that had appeared in the earliest work on quantum theory. This was not a limitation of measurement technology. It was not that our instruments were too crude to measure both quantities simultaneously. It was a fundamental feature of nature. Position and momentum were not both simultaneously definite. If a particle had a precisely defined position, its momentum was fundamentally indeterminate, not unknown, but genuinely undefined. If it had a precisely defined momentum, its position was everywhere at once. This is the Heisenberg uncertainty principle, and it is one of the deepest statements in all of physics. It means that the idea of a particle, something with a definite position and a definite velocity at any given moment, is not something that exists in the quantum world. Particles, in the classical sense, do not exist at that level. What exists are quantum objects with probabilistic properties, described by wave functions that spread through space and evolve according to precise mathematical laws. The certainty we feel about the world, the sense that things are where they are, that a particle is moving in a particular direction at a particular speed, is a property of the large-scale world we inhabit, where quantum effects average out over the enormous numbers of atoms involved in any ordinary object. It is not a property of the fundamental level of reality. At the fundamental level, nothing is certain until it is measured. And even then, some things remain uncertain forever. Planck's constant, the number that appears in the uncertainty principle and in almost every equation of quantum mechanics, is extraordinarily small. Its value is approximately 6.626 times 10 to the power of negative 34 joule-seconds. This is a number so small that it is essentially impossible to develop any intuitive sense of its magnitude. It is smaller than small. It is the reason why quantum effects are invisible in everyday life. For large objects, objects made of many atoms moving at ordinary speeds, the quantum uncertainties are so tiny relative to the scale of the object that they are completely undetectable. A thrown ball has a quantum uncertainty in its position that is smaller than a proton by many orders of magnitude. It might as well not exist. But for electrons and for other subatomic particles, the situation is entirely different. The mass of an electron is about 9 times 10 to the power of negative 31 kilograms, another extraordinarily small number. When you calculate the quantum uncertainty in an electron's position under typical conditions, you get numbers that are comparable to the size of an atom itself. The uncertainty is not a negligible correction, it is the whole story. The electron's position is fundamentally smeared out over a volume comparable to the atom it inhabits. This is why atoms have the structure they do. Electrons do not orbit nuclei the way planets orbit the Sun, following precise trajectories. They inhabit regions of space, orbitals described by probability distributions. The electron in a hydrogen atom does not travel along a fixed circular path. It is, in some sense, simultaneously everywhere within its orbital. The orbital is not a path, but a probability cloud, a description of where the electron is likely to be found if you were to measure its position at a given moment. And the specific shapes of these probability clouds, which determine the size of atoms and the way they bond to one another, and therefore the structure of all chemistry and all biology and all the material world, are determined directly by quantum mechanics. The shapes emerge from the mathematics of the wave function, from the uncertainty principle, from the discrete energy levels that Bohr had first glimpsed. Everything about the structure of matter at the level where chemistry lives is quantum mechanical. The table you are imagining, and the hand you are imagining pressing against it, and the atoms they are made of, and the electrons whose repulsion gives rise to the sensation of solidity. All of it is quantum mechanical, all the way down. There is one more phenomenon to introduce before we go deeper still, and it is perhaps the strangest of all. It is called quantum tunneling. Consider a particle, an electron say, approaching a barrier. In classical physics, the outcome is simple. If the particle has enough energy to get over the barrier, it passes through. If it does not have enough energy, it is reflected. This is just like a ball rolling toward a hill. If it has enough momentum, it crests the hill. If not, it rolls back. In quantum mechanics, this is not what happens. Because the electron is described by a wave function that extends through space, some of the wave function extends into and through the barrier, even if the electron does not have enough energy to pass over it classically. The probability of finding the electron on the other side of the barrier is not zero. There is a small but definite chance that the electron will simply appear on the other side, that it will tunnel through the barrier as if the barrier were not there. This is quantum tunneling, and it is not a theoretical curiosity. It happens constantly, in devices and in nature, and the world depends on it in ways you might not expect. The sun shines because of quantum tunneling. In the core of the sun, hydrogen nuclei, protons, are being fused together to form helium. But protons are positively charged, and like charges repel each other. To fuse two protons, you need to bring them close enough for the strong nuclear force, which operates only at extremely short range, to take over and bind them. But getting them that close requires overcoming the electromagnetic repulsion between them, which demands enormous energy. The core of the sun is very hot indeed, about 15 million degrees Celsius. But even at that temperature, the protons in the solar core do not have enough energy, on average, to overcome the electromagnetic repulsion between them. By classical physics, the sun should not be able to fuse hydrogen at all. The temperature is too low. The protons should bounce off each other long before they get close enough to fuse. But they do fuse. The sun shines. Life on Earth exists. And the reason is quantum tunneling. The wave functions of the protons extend through the electromagnetic barrier between them. There is a small but finite probability that two protons will find themselves on the fused side of the barrier without ever having had enough energy to get there classically. And with the enormous numbers of protons in the solar core and the 4.5 billion years the sun has had to accumulate these events, that small probability adds up to the energy output of a star. The light falling on your face on a summer afternoon, the warmth you feel when you step outside, the photosynthesis that built every plant that ever grew on this planet. All of it traces back to quantum tunneling events happening in the core of the sun, one proton at a time, each one a small impossible act of quantum strangeness that classical physics says should not occur. Quantum tunneling also happens in your body. The chemical reactions that sustain life, the breaking and forming of chemical bonds, the transfer of electrons between molecules, the processes by which enzymes catalyze reactions, all of these involve quantum effects. Electrons tunnel between molecules. Protons tunnel in biochemical processes. The speed and efficiency of these reactions, and therefore the speed and efficiency of life itself, depend on quantum mechanical effects that have no classical explanation. There is evidence that quantum tunneling plays a role in the action of enzymes, the proteins that accelerate chemical reactions in living cells. Some enzymes are so efficient that classical physics cannot fully account for their speed. The most likely explanation is that they are harnessing quantum tunneling, allowing protons and electrons to take shortcuts through energy barriers that classical mechanics says are impassable. There is evidence too that the process of photosynthesis, by which plants and bacteria convert sunlight into chemical energy, involves quantum coherence. When a photon of light is absorbed by a photosynthetic complex, the energy needs to be transferred from the place where it is absorbed to the reaction center where it can be used. This transfer happens with an efficiency that is difficult to explain classically. Experiments suggest that the energy explores multiple pathways simultaneously, in quantum superposition, finding the most efficient route through a process that has some of the character of quantum computation. Life, in other words, is not just made of atoms whose behavior is governed by quantum mechanics. Life actively uses quantum mechanics. Evolution, over billions of years, has found ways to harness the strangeness of the quantum world, its tunneling, its superposition, its coherence, to build the machinery of biology. The quantum world is not something separate from the biological world, it is its foundation. It is late now or early, depending on how you think about time. The room around you is quiet. Whatever light there was has faded or been extinguished, and the darkness is soft and complete. Your breathing has slowed. The thoughts that were busy and insistent a little while ago have begun to soften at their edges, to lose their urgency, to drift. We have come a long way from that table. We began with the solid, familiar surface of an ordinary object in an ordinary room. We descended step by step into the structure of matter, past the scale of molecules and atoms into the interior of the atom itself. We found that the atom is almost entirely empty space, that the solidity of things is an electromagnetic illusion, that the electrons orbiting the nucleus are not the simple particles we might have imagined, but quantum objects described by probability waves, constrained to specific energy levels, jumping between them in discrete, instantaneous leaps. We found that electrons, and all quantum objects, exist in superposition before they are measured, that they pass through both slits simultaneously, that the act of measurement collapses their possibilities into a single outcome, that this collapse cannot be predicted with certainty, that the universe at its deepest level is irreducibly probabilistic. We found that there is a fundamental limit to what can be known about a quantum system, that position and momentum cannot both be defined simultaneously, that certainty in one implies uncertainty in the other, that this is not a failure of measurement but a feature of reality. And we found that this strange, probabilistic, wave-like quantum reality is not confined to the laboratory. It operates in the sun, sustaining the nuclear fusion that lights our days. It operates in our cells, enabling the chemical reactions that sustain our lives. It is everywhere, always, invisible, but essential. There is more to explore. The quantum world extends deeper than we have gone, into the interior of protons and neutrons, into the fields that pervade all of space, into the strange territory where quantum mechanics and relativity meet, and the mathematics begins to break down in ways that physicists are still working to understand. There is the phenomenon of quantum entanglement, which Einstein called spooky action at a distance, in which two particles can be correlated across any distance whatsoever in ways that seem to defy the ordinary structure of space and time. There is the question of what the wave function really is, whether it describes something physically real or only our knowledge of a system, and what exactly happens when it collapses, and why the quantum world of superposition and probability gives rise to the classical world of definite objects and determined outcomes that we inhabit. These are questions we will explore, but not tonight. Tonight it is enough to have descended this far, to have looked through the surface of things and seen the emptiness and the strangeness that lies beneath, to know that the table and the hand and the darkness of the room and the slow rhythm of your breathing are all, at their deepest level, made of quantum stuff, probabilistic, wave-like, uncertain, and extraordinary. Let that knowledge settle into you as you settle into sleep. The quantum world will be here when you return. And here it is, still waiting, still operating beneath the surface of everything, indifferent to the hours that have passed or not passed, unchanged and unchanging in its fundamental strangeness. The electrons in the atoms of the ceiling above you are still smeared across their probability clouds. The nuclei at the center of those atoms are still held together by forces that operate according to rules unlike anything in ordinary experience. The photons streaming through the darkness, the infrared radiation emitted by warm surfaces, the faint light from distant sources, are still behaving as both waves and particles, still refusing to be one thing or the other. Nothing has changed while you were away. We were descending. We had reached the interior of the atom and found it almost entirely empty. We had found the electron, not the simple orbiting particle of popular imagination, but a quantum object inhabiting a probability cloud, constrained to specific energy levels, jumping between them without passing through the space in between. We had found superposition and the uncertainty principle and quantum tunneling, the impossible passage of particles through barriers they do not have the energy to cross. We go deeper now. There is more to the atom than electrons. The nucleus, that tiny, impossibly dense region at the center, 100,000 times smaller than the atom itself, contains its own strange world. And within the nucleus, inside the protons and neutrons that compose it, there is a level of structure that was entirely unsuspected for most of the 20th century. A level at which the quantum world reveals new dimensions of its strangeness. But before we descend to that level, there is something else we need to understand. Something that changes the picture we have been building in a fundamental way. Something that Einstein himself found so disturbing that he spent the last decades of his life trying to argue it away. It is called quantum entanglement. In 1935, Albert Einstein, together with two colleagues named Boris Podolsky and Nathan Rosen, published a paper that was intended as an argument against quantum mechanics. Einstein had never been comfortable with quantum theory, despite having contributed centrally to its development. His discomfort was not with the mathematics. The calculations were clearly correct, and he knew it. His discomfort was with what the mathematics seemed to imply about the nature of reality. Specifically, he objected to the idea that a quantum system did not have definite properties until it was measured. He believed, deeply, almost as a matter of principle, that the physical world had a definite state independent of any observer. Things were what they were, whether or not anyone was looking at them. The paper he published with Podolsky and Rosen described a thought experiment designed to show that quantum mechanics must be incomplete. Consider two particles that interact with each other and then fly apart in opposite directions. Quantum mechanics says that certain properties of these particles, their spins for instance, are correlated but individually undefined until measured. Each particle exists in a superposition of possible spin states. When you measure one, it collapses to a definite state, and the other instantly collapses to a correlated state, no matter how far apart the two particles are. Einstein found this unacceptable. If measuring one particle instantly determined the state of the other, regardless of distance, that seemed to imply that information was traveling between them faster than light, which relativity forbids. He concluded that the particles must have had definite spin states all along, that the quantum description was simply incomplete, missing some hidden variable that, if known, would make the outcome of each measurement predictable. This seemed reasonable. It seemed like the sane interpretation. A particle either has this spin or that spin, and measuring it simply reveals what was already the case. Quantum mechanics just doesn't know about the hidden variable. For 30 years, this remained a matter of philosophical debate, because no experiment could distinguish between the two interpretations. Then, in 1964, a physicist named John Bell published a paper that changed everything. Bell showed that the two interpretations, hidden variables versus genuine quantum indeterminacy, made different predictions that could, in principle, be tested. He derived a mathematical inequality, now called Bell's inequality, that any theory based on hidden local variables must satisfy. If quantum mechanics was correct, the inequality would be violated, and the inequality could be tested by measuring the correlations between entangled particles. Over the following decades, a series of increasingly refined experiments were conducted. The results were unambiguous. Bell's inequality was violated. The correlations between entangled particles were stronger than any local hidden variable theory could produce. Einstein was wrong. The particles did not have definite spin states before measurement. The correlation was not the result of hidden information carried by the particles from their moment of interaction. When you measured one particle and it collapsed to a definite state, something really did happen to the other particle, instantly, regardless of distance. This is quantum entanglement, and it is real. But what does it mean? This is where things become genuinely difficult to put into words, because what entanglement implies about the structure of reality is something for which ordinary language provides no good framework. It does not mean that information travels faster than light. This is important and worth being clear about. You cannot use entanglement to send a message. When you measure one of a pair of entangled particles and it collapses to a definite state, the outcome is random. You get, say, spin up. The distant particle instantly becomes spin down. But you cannot control which outcome you get. And because the outcome is random, your partner at the other end cannot learn anything from it that they could not have learned by chance. The correlation only becomes apparent when you compare results, and comparing results requires ordinary communication, which is limited by the speed of light. So entanglement does not allow faster than light communication, but it does imply something profound about the relationship between distant parts of the universe. It implies that the universe is, in some sense, non-local. That separated particles can be correlated in ways that cannot be explained by any information they carried with them when they separated. That the quantum state of a particle is not entirely a property of that particle alone, but is partly defined by its relationship to other particles with which it has interacted, regardless of how far away those particles now are. The physicist John Bell put it this way: the universe is not locally causal. Things that happen here can be correlated with things that happen there in ways that cannot be explained by any local mechanism. Any mechanism that involves only information traveling through the space between them at or below the speed of light. What actually connects the entangled particles is not entirely clear. Some physicists think the wave function itself, the mathematical object that describes the quantum state of a system, is physically real, and that an entangled pair of particles is described by a single wave function that spans the space between them, connecting them regardless of distance. Others think the wave function is not a physical object, but a mathematical tool, and that the correlations between entangled particles are simply a feature of the way reality is structured, not something that needs a mechanism to explain it. What is clear is this: the universe at the quantum level does not respect the common sense picture of separated objects with independently defined properties. Particles that have interacted remain connected. Their fates are intertwined across space in ways that have no classical explanation. The world is more deeply interconnected than it appears. Entanglement is not merely a curiosity of physics experiments, it has become the basis for a new field of technology, quantum information science, that is, in the early 21st century, beginning to move from theoretical possibility to practical reality. The most discussed application is quantum computing. An ordinary computer stores information as bits. Each bit is either 0 or 1. A quantum computer stores information as qubits, quantum bits. A qubit can be in a superposition of 0 and 1 simultaneously, just as an electron can be in a superposition of spin up and spin down. When you perform an operation on a qubit, you perform it on both states at once. With 2 qubits, you can represent 4 states simultaneously. With 3, 8. With n qubits, you can represent 2 to the power of n states simultaneously. For a quantum computer with just 300 qubits, that is more states than there are atoms in the observable universe. This exponential scaling gives quantum computers a potential advantage over classical computers for certain types of problems. Problems where you need to search through an enormous number of possible solutions, or where the solution involves finding patterns in very large data sets. The most famous example is factoring large numbers, which is the basis of most modern encryption. A classical computer would take longer than the age of the universe to factor a number with thousands of digits. A quantum computer, using an algorithm developed by Peter Shor in 1994, could do it in hours. Quantum cryptography is another application. Quantum mechanics guarantees that you cannot measure a quantum system without disturbing it. This means that if 2 people exchange a cryptographic key using quantum particles, any eavesdropper who tries to intercept the key will inevitably disturb the particles, and the disturbance will be detectable. Quantum cryptography promises, in principle, communication that is provably secure against any eavesdropper, not merely computationally difficult to crack, but physically impossible to intercept without detection. These technologies are still in their early stages. Maintaining quantum coherence, keeping qubits in their delicate superposition states long enough to perform useful computations, is extraordinarily technically difficult. Quantum systems are fragile. The slightest interaction with the surrounding environment can cause a qubit to decohere, to lose its quantum properties and collapse to a classical state. Physicists and engineers are working on ways to shield qubits from environmental disturbance and to correct the errors that decoherence introduces. But the progress has been rapid. Quantum computers with hundreds of qubits exist. Certain narrow computational tasks have been performed by quantum computers faster than any classical machine could achieve them. The field is moving quickly, and the quantum world, that strange counterintuitive reality that physicists spent the early 20th century struggling to understand, is becoming, in the early 21st century, an engineering domain. We have been moving so far in one direction, downward, into the atom, into the nucleus, toward the smallest scales. But there is another direction we have not yet explored, and it is perhaps equally illuminating. Outward. The quantum world is not only the world of the very small. Quantum effects manifest at every scale. The reason they are invisible in everyday life is not that they don't apply to large objects, but that large objects are made of enormous numbers of particles, and the quantum effects of individual particles average out in ways that produce the apparently classical behavior we observe. But there are circumstances in which quantum effects manifest at scales far larger than individual atoms, and these provide some of the most striking demonstrations of the quantum world's reality. Consider superconductivity. Most metals conduct electricity with some resistance. As electrons move through the metal, they collide with the atoms in the metal's crystal lattice, losing energy and generating heat. This is why electrical wires warm up when current flows through them. The resistance is a consequence of the chaotic, individual behavior of electrons moving through an imperfect medium. But certain materials, when cooled below a critical temperature, undergo a dramatic transformation. Their electrical resistance drops to exactly zero, not nearly zero, exactly zero. A current set flowing in a loop of superconducting material will flow forever, without diminishing, without generating any heat, because there is nothing to resist it. This phenomenon, superconductivity, was discovered in 1911 and was not understood for nearly half a century. The explanation, when it finally came in 1957, was purely quantum mechanical. At low temperatures, electrons in a superconductor form pairs. called Cooper pairs, after Leon Cooper, who first described them. This pairing happens because of a subtle quantum mechanical interaction between the electrons and the vibrations of the crystal lattice. The paired electrons enter a collective quantum state, a single quantum mechanical entity described by a single wave function that extends across the entire superconductor. They move together, coherently, in perfect synchrony. Because they move as a single quantum object, they cannot be scattered by individual impurities or lattice vibrations in the way that unpaired electrons are. The quantum coherence that makes individual particles behave as waves makes the entire Cooper pair condensate impervious to the mechanisms that cause ordinary electrical resistance. The current flows without resistance because the entire electron fluid has become, in a precise quantum mechanical sense, a single thing. Superconductivity is a macroscopic quantum phenomenon. Quantum mechanics made visible at the scale of an ordinary piece of wire. It is used today in MRI machines, in particle accelerators, and in sensitive scientific instruments. Every time a patient lies in an MRI scanner and the machine images the interior of their body, they are benefiting from a technology whose operating principle is the quantum coherence of electron pairs at low temperature. There is another macroscopic quantum phenomenon that is, in some ways, even more striking. It is called a Bose-Einstein condensate. Quantum particles come in two types, distinguished by a property called spin. Particles with half-integer spin, electrons, protons, neutrons, are called fermions. They obey a rule called the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state simultaneously. This rule is why electrons in an atom are arranged in shells rather than all collapsing to the lowest energy level. It is why matter is solid. Electrons in different atoms cannot occupy the same state, so atoms resist being pushed together. Particles with integer spin, photons, certain atoms, are called bosons. They do not obey the exclusion principle. Multiple identical bosons can occupy the same quantum state simultaneously. Not just can, they actively prefer to. There is a quantum mechanical tendency for bosons to pile up in the same state, an effect that becomes increasingly strong as more particles occupy that state. In 1924, Satyendra Nath Bose and Albert Einstein worked out the theoretical consequences of this tendency. They predicted that at sufficiently low temperatures, a collection of bosonic atoms would undergo a phase transition. Essentially, all of the atoms would simultaneously fall into the same lowest energy quantum state, forming a single quantum entity, a Bose-Einstein condensate. It was a remarkable prediction. But the temperatures required were so low, fractions of a degree above absolute zero, that achieving them experimentally seemed impossible for decades. Absolute zero, the temperature at which all thermal motion would cease, is minus 273.15 degrees Celsius. A Bose-Einstein condensate requires temperatures of a millionth of a degree above that, or colder. In 1995, using a combination of laser cooling and magnetic trapping techniques developed over the previous decade, two groups of physicists, one in Colorado, one in Massachusetts, achieved temperatures low enough and produced the first Bose-Einstein condensates. The achievement won the Nobel Prize in 2001. A Bose-Einstein condensate is, in a precise sense, a quantum object made of millions of atoms. The individual atoms lose their individual identities and merge into a single quantum mechanical entity, described by a single wave function, behaving as a single thing. It is quantum mechanics operating not at the scale of a single particle, but at the scale of something large enough to be photographed. When physicists take images of a Bose-Einstein condensate and watch how it behaves, how it flows without viscosity, how it exhibits interference patterns, how it responds to perturbations. They are watching quantum mechanics in action at a scale that bridges the quantum and the classical. They are seeing with their own eyes the wave nature of matter that de Broglie predicted in 1924. We have now descended far enough into the quantum world to see several of its most fundamental features clearly. Superposition, entanglement, the uncertainty principle, tunneling, the wave nature of matter, the discrete, probabilistic character of quantum events. These are the signature features of quantum mechanics, the features that distinguish it from classical physics and that make it so difficult to reconcile with ordinary intuition. But we have not yet reached the bottom. Below the level of atoms, inside the nucleus, there is a deeper layer of structure, and it operates according to a version of quantum mechanics that is, in certain ways, even stranger than what we have described so far. The nucleus of an atom is made of protons and neutrons. A hydrogen nucleus consists of a single proton. A helium nucleus has 2 protons and 2 neutrons. Carbon has 6 of each. The heaviest naturally occurring element, uranium, has 92 protons and between 143 and 146 neutrons, depending on the isotope. Protons have a positive electric charge. Neutrons have no charge. Both are roughly 2,000 times more massive than an electron. They are packed together in the nucleus at densities that are almost unimaginable. Nuclear matter is so dense that a teaspoon of it would weigh about 1 billion tons on Earth. What holds the nucleus together? The protons, all positively charged, should repel each other violently. The electromagnetic repulsion between them at nuclear distances is enormous. Something else must be acting to overcome it and bind the nucleus together. That something is the strong nuclear force, the strongest of the 4 fundamental forces of nature, and one that operates only at the extremely short ranges inside and around the nucleus. The strong force is entirely quantum mechanical. It is described by a theory called quantum chromodynamics, which was developed in the 1970s and is one of the most successful theories in the history of physics. And here is where the deeper layer of structure comes in. Protons and neutrons are not elementary particles. They are made of something smaller. In the 1960s, experiments at the Stanford Linear Accelerator Center began probing the interior of protons by firing high-energy electrons at them. The electrons would scatter off the proton's interior, and the pattern of scattering would reveal something about what was inside. What they found, in a series of experiments that are, in the history of physics, as consequential as Rutherford's discovery of the nucleus, was that the proton had an internal structure. It contained smaller, point-like constituents that scattered the electrons at large angles, just as the nucleus had scattered Rutherford's alpha particles. These constituents were called quarks. The word was chosen by the physicist Murray Gell-Mann, who took it from a line in James Joyce's Finnegan's Wake, ___, quote _0, ___. There are 6 types of quarks called up, down, strange, charm, bottom and top. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. The quarks are held together by particles called gluons, which carry the strong force between them. Quarks have electric charges that are fractions of the proton's charge. Up quarks carry a charge of positive 2/3. Down quarks carry a charge of negative 1/3. The 3 quarks in a proton, 2 up, 1 down, add up to a total charge of positive 1, which is the proton's charge. The 3 quarks in a neutron add up to 0, which is why neutrons are electrically neutral. But quarks have another property entirely unlike anything in ordinary experience. It is called color charge, and it is the source of the strong force. Color charge has nothing to do with visible color. The name is simply an analogy. Quarks come in 3 varieties of this property, called red, green, and blue. And the rule is that all observable particles must be color neutral. Just as complementary colors of light add up to white, the 3 color charges of the quarks in a proton add up to something color neutral. This rule is why quarks are always found in groups of 3, or in quark-antiquark pairs, and never alone. The gluons that carry the strong force between quarks are themselves color-charged. This is unlike photons, which carry the electromagnetic force but have no electric charge themselves. Because gluons carry color charge, they can interact with each other. Gluons can exchange gluons. This gives the strong force properties that are very different from electromagnetism. One of the most striking properties is called confinement. The strong force, unlike gravity or electromagnetism, does not diminish with distance in the ordinary way. Instead, as you try to pull 2 quarks apart, the force between them remains roughly constant, like a rubber band that does not get weaker as it stretches. The energy required to separate 2 quarks completely is so enormous that before they can be separated, the energy creates new quark-antiquark pairs from the vacuum itself. You pull on a quark, and instead of freeing it, you find that you have created new particles. This is why free quarks have never been observed. No matter how energetically you probe nuclear matter, quarks always come in groups. They are permanently confined inside the particles they make up. The theory that describes quarks and gluons, quantum chromodynamics, is part of a larger framework called the Standard Model of Particle Physics. The Standard Model is, by any measure, one of the most successful scientific theories ever developed. It describes all of the known elementary particles and 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, within a single unified mathematical framework. The particles of the Standard Model fall into 2 categories. Fermions, the matter particles, include the quarks, 6 types, and the leptons, 6 types, including the electron and the neutrino and their heavier cousins. Bosons, the force-carrying particles, include the photon, which carries electromagnetism, the gluons, which carry the strong force, the W and Z bosons, which carry the weak force, and the Higgs boson. The Higgs boson deserves special mention. It was predicted in 1964 by Peter Higgs and independently by several other physicists. Its existence was required by the mathematical consistency of the Standard Model, specifically by the mechanism through which the W and Z bosons acquire their mass. But it was not observed directly until 2012, when experiments at the Large Hadron Collider at CERN in Geneva detected it. The discovery of the Higgs boson was the confirmation of a prediction that had taken nearly 50 years to test. It was a triumph for theoretical physics, and for the extraordinary enterprise of building a machine 17 miles in circumference and operating it at energies never achieved in any laboratory in order to produce, for fractions of a second, conditions that last existed in the universe a trillionth of a second after the Big Bang. The Standard Model, however, is not the final word. It does not include gravity, the 4th fundamental force, which is described by Einstein's general theory of relativity. Despite enormous effort, no one has succeeded in constructing a quantum theory of gravity that is mathematically consistent and agrees with experiment. General relativity treats space-time as a smooth, continuous entity that curves in response to mass and energy. Quantum mechanics treats everything else as made of discrete, probabilistic quanta. When you try to apply the quantum framework to gravity, the mathematics breaks down, producing infinities and inconsistencies that physicists have been struggling with for nearly a century. The reconciliation of general relativity and quantum mechanics is, many physicists believe, the deepest unsolved problem in theoretical physics. It is the gap at the center of our understanding of reality, the place where our two best theories meet and fail. We have been descending for a long time now. We have gone from the surface of things, from the table, the hand, the room, down through molecules and atoms, through electrons and nuclei, through protons and neutrons, and down to quarks and gluons. We have followed the structure of matter to the smallest scales currently accessible to experiment and found it strange at every level. But there is one more place to go, not smaller, sideways in a sense, into the nature of empty space itself, between the particles, between the atoms in your body, between the quarks inside those atoms, between the electrons and the nucleus in each atom, there is space. Space that appears from the outside to be empty, nothing. But in quantum mechanics, there is no such thing as truly empty space. This is one of the most profound and counterintuitive consequences of the uncertainty principle. Consider the uncertainty principle as applied not to a particle's position and momentum, but to energy and time. There is an analogous uncertainty relation. The more precisely you specify the energy of a system, the less precisely you can specify when it has that energy, and vice versa. This means that even in a region of space that contains no particles, even in a vacuum, the energy cannot be exactly zero. If the energy were exactly zero, you would know it precisely, which would require an infinite precision in time, which the uncertainty principle forbids. Instead, the energy of empty space fluctuates. It goes up and down rapidly and randomly, on timescales so short that they are inversely proportional to the magnitude of the fluctuation. These fluctuations are not nothing. They have physical consequences. For very brief moments measured in tiny fractions of a second, the fluctuating energy of the vacuum is large enough to spontaneously create pairs of particles from nothing. A particle and its antiparticle pop into existence together, exist for the briefest possible moment, and then annihilate each other and vanish. They are called virtual particles, and they are a continuous feature of empty space. The vacuum is not empty. It seethes with virtual particles, constantly appearing and disappearing, a quantum foam of transient matter and antimatter flickering in and out of existence too quickly to be directly observed. These virtual particles are not hypothetical. They have measurable effects. One of the most precise measurements in physics is a quantity called the anomalous magnetic moment of the electron, a tiny deviation in the electron's magnetic properties from what a simple theory would predict. The deviation is caused by the electron's interaction with the virtual particles in the vacuum around it, the constant flickering cloud of transient particles that surround every real particle at every moment. When physicists calculate this deviation using quantum electrodynamics, taking into account the contributions of virtual particles, they get a result that agrees with experiment to better than 1 part in a trillion. It is the most precisely confirmed theoretical prediction in the history of science. Virtual particles also produce a phenomenon called the Casimir effect, which was predicted in 1948 and experimentally confirmed in 1997. If you place 2 metal plates very close together in a vacuum, the virtual particles between the plates are constrained. Only certain wavelengths fit in the gap. Outside the plates, all wavelengths are present. The result is that there are more virtual particles pushing on the outside of the plates than between them, and the plates are pushed together by an extremely small but measurable force. The Casimir effect is, in a sense, the force of nothing. The pressure of virtual particles that do not quite exist, pushing real objects together across a vacuum that is not quite empty. The vacuum, then, is alive with quantum activity. It is not a passive backdrop against which particles move. It is a dynamic, fluctuating medium that interacts with everything in it. This picture of the vacuum is central to quantum field theory, the framework that underlies the Standard Model, and is, in the view of most physicists, the deepest description of physical reality we currently have. In quantum field theory, the fundamental entities are not particles, but fields. Fields that pervade all of space. An electron field, a quark field, a photon field, a Higgs field. These fields extend everywhere, through your body, through the Earth, through the space between galaxies. They exist in every cubic centimetre of space simultaneously. Particles are not objects that travel through these fields. Particles are excitations of the fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Just as a wave on the ocean is not a separate thing from the ocean but a disturbance in it, an electron is not a separate thing from the electron field but a disturbance in it. This reframing is more than a change of language. It changes what we mean by a particle. In quantum field theory, particles can be created and destroyed. They can appear from and disappear into the vacuum because they are excitations of fields that are always present. When a particle meets its antiparticle and they annihilate, what is really happening is that two excitations of the field cancel each other out and the field returns to its ground state. When two photons collide and produce an electron-positron pair, what is really happening is that energy from the photon field is transferred to the electron field, raising it from its ground state to an excited state, creating two particles. The vacuum itself is the ground state of all the quantum fields. It is not empty. It is the baseline from which all the richness of matter and energy emerges. The virtual particles that flicker in and out of existence are the quantum fluctuations of the fields around their ground states. In this picture, the universe is not made of stuff. It is made of fields. The things we call particles are patterns in those fields. Fleeting, transient disturbances that exist as long as they have energy to sustain them, and then dissolve back into the ground state from which they emerged. There are no separate individual objects. There are only fields, and the excitations of fields. This is as deep as we can currently go. The quantum fields of the Standard Model, the electron field, the quark fields, the Higgs field, the gauge fields that carry the forces, are, by our best current understanding, the most fundamental level of physical reality. Everything you have ever seen or touched or thought about is a pattern in these fields. The table, the hand, the air in the room, the neurons firing as you drift towards sleep, all of it, at its deepest level, is an excitation of quantum fields pervading all of space. There is one more thing to say before we rest. We have been exploring the quantum world as a place, as a level of reality that exists beneath the familiar surface of things, accessible to physicists with their experiments and their mathematics, and it is that. But it is also something more. The quantum world is not merely the small-scale machinery of the universe. It is the reason the universe has the character it does, the reason stars shine, the reason chemistry exists, the reason life is possible. Consider for a moment what a world without quantum mechanics would look like. Without the uncertainty principle, electrons would spiral into nuclei and atoms would collapse. Without quantum mechanics, the specific energy levels of atoms, the levels that determine what wavelengths of light they emit and absorb, would not exist, and the precise structured chemistry that builds molecules and proteins and cells would be impossible. Without quantum tunneling, nuclear fusion in stars would not occur, and stars would not shine. Without the Pauli exclusion principle, electrons would all collapse to the lowest energy state and matter as we know it. Solid, structured, differentiated, would not exist. Everything would be a uniform, undifferentiated soup. Quantum mechanics is not a feature of the universe at its edges. It is the framework that makes the universe possible. The quantum world and the everyday world are not two separate worlds. They are the same world, seen at different scales. The strange rules of the quantum level, the superposition, the entanglement, the uncertainty, the discreteness, are the rules from which the familiar surface of reality emerges. The solid table is a consequence of quantum mechanical forces. The warmth of sunlight is a consequence of quantum tunneling. The color of flowers, which determines what wavelengths of light the molecules in their petals absorb and reflect, is a consequence of quantum energy levels. The fire of consciousness, if it is anything, and this remains an open question of profound depth, is a consequence of quantum processes in the neurons of the brain. You are quantum mechanical in all the way through. Not in the sense that your behavior is directly governed by quantum uncertainty in the way that individual electrons are. At the scale of the body, quantum effects average out, and your movements and decisions are, as far as anyone can tell, classical. But in the sense that the matter you are made of, the forces that hold your atoms together, the chemistry that sustains your cells, the light by which you see the world, all of it runs on quantum mechanics. All of it is, at its foundation, the behavior of quantum fields and their excitations, playing out according to the strange, precise, probabilistic rules of the quantum world. The room is very quiet now. Whatever sounds there were, the distant movement of traffic, the small sounds a building makes as it settles into the night, the particular silence of a late hour, have faded or been absorbed into something deeper. The darkness around you is soft and complete. You have been lying still for a long time, and your body has grown heavy in the way that bodies do when the boundary between waking and sleeping begins to dissolve. We have travelled far tonight. From the surface of an ordinary table, down through layer after layer of reality, we have descended to the quantum fields that underlie everything. We have met electrons and photons, protons and neutrons, quarks and gluons, virtual particles and the seething vacuum. We have encountered superposition and entanglement, uncertainty and tunneling, the discrete energy levels of atoms and the continuous fields that give rise to them. We have found that the world is stranger and deeper and more intricately structured than it appears. That the solidity of things is an electromagnetic illusion, that particles are not really particles, but excitations of fields, that empty space is not empty, that the separation between distant objects is, in the quantum sense, less absolute than it seems. That certainty is not a feature of the fundamental world, only of the large-scale averages that we inhabit. We have found, too, that this strangeness is not something alien or hostile. It is the ground of everything. It is the reason the world is as it is, structured and chemical and warm and alive. The quantum world is not something other than our world. It is our world seen clearly. There is one more layer to explore. The deepest questions about why these particular quantum fields exist, about where the laws of quantum mechanics themselves come from, about what happened in the very first moments of the universe when all the fields were compressed into an unimaginably hot and dense state. These questions wait for us. They wait for another time, for another descent. For now, the quantum fields are humming their quiet hum beneath the surface of everything. The virtual particles are flickering in and out of the vacuum. The electrons in the atoms of your body are inhabiting their probability clouds. The quarks inside your protons are being held together by gluons exchanging color charge across distances smaller than anything that has ever been seen. All of this is happening constantly, at every scale, in every atom of every object in the room, and it will continue unchanged while you sleep. Let it carry you. The quantum fields are humming their quiet hum beneath the surface of everything. You have been here before, in this stillness, in this darkness. The room around you has not changed. The atoms in the walls and the floor and the ceiling are where they were. The electrons are still inhabiting their probability clouds. The quarks are still bound inside protons and neutrons by gluons exchanging color charge at speeds approaching that of light, across distances so small that no instrument ever built has come close to resolving them. The virtual particles are still flickering in and out of the vacuum, appearing and disappearing in intervals so brief they are measured in units that have no analogue in ordinary experience. All of this was happening while you slept, if you slept. All of this will be happening long after this moment has passed. We have come a long way. We descended from the surface of an ordinary object into the atom, and from the atom into the nucleus, and from the nucleus into the quarks, and from the quarks into the quantum fields that underlie everything. We found superposition and entanglement and uncertainty and tunneling. We found that particles are not objects but excitations. We found that empty space is not empty but seethes with virtual activity. We found that the world at its foundation is nothing like what it appears to be from the surface. There is one more layer, or rather, there is one more direction, not downward into smaller scales, but inward into the questions that quantum mechanics raises about the nature of reality itself. The questions that are not about what quantum mechanics predicts, but about what it means. The questions that have occupied the best minds in physics for a century and remain even now unresolved. And beyond those questions, there is the place where quantum mechanics meets the very largest scale of all, the birth of the universe itself, the moment, if it was a moment, from which everything else followed. We go there now, slowly. There is no hurry. We have mentioned in passing the measurement problem. It is time to face it directly. Quantum mechanics is a theory of extraordinary precision and power. Its predictions have been confirmed to greater accuracy than any other theory in the history of science. Its mathematical structure is elegant and consistent. And yet, at its center, there is something that no one has been able to explain satisfactorily in 100 years of trying. The problem is this. The quantum state of a system is described by a wave function. The wave function evolves in time according to a precise equation, the Schrödinger equation, in a way that is perfectly deterministic and perfectly smooth. The wave function of an electron, for instance, spreads out through space in a continuous wave-like manner, describing the probability of finding the electron in various locations. When you measure the electron, when you interact with it in a way that forces it to have a definite position, the wave function collapses. The electron is found in a single location. The spread-out probability cloud is gone. In its place is a definite result. But this collapse is not described by the Schrödinger equation. It is something different, something that happens suddenly, discontinuously, outside the normal flow of quantum evolution. And no one has been able to explain, in terms of the underlying quantum theory, exactly when it happens, or why, or what exactly constitutes a measurement. Is a measurement any interaction between a quantum system and a classical device? But there are no truly classical devices. All devices are made of atoms, which obey quantum mechanics. Is a measurement any interaction that produces an irreversible record somewhere in the environment? This is a more promising idea, called decoherence, and we will return to it. Is a measurement something that happens when a conscious observer becomes aware of a result? Some physicists have seriously entertained this possibility, though most find it unsatisfying. The measurement problem is not merely a philosophical puzzle, it cuts to the heart of what quantum mechanics is actually describing. Is the wave function a real physical object that exists in space? Or is it only a mathematical tool for calculating probabilities? a description of what we know rather than of what is. If the wave function is real, then what happens to all the other branches of it when it collapses? All the branches corresponding to the outcomes that were not observed? If it is not real, then what is? Physicists have proposed many interpretations of quantum mechanics, many answers to these questions. None of them has been universally accepted. Each resolves some of the difficulties while introducing others. They are all mathematically equivalent, they all make the same predictions, but they describe different underlying realities, and the question of which one is correct, if any of them are, cannot currently be answered by experiment. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s, was the first and for a long time the dominant answer. Bohr's position was, at its core, a kind of philosophical pragmatism. The wave function, he argued, is not a description of reality. It is a description of what we can predict about the outcomes of measurements. Questions about what is really happening between measurements, about what the electron is doing when no one is looking, are not meaningful questions. Physics describes observations, not an underlying reality independent of observation. This view is sometimes called anti-realism about the wave function. It sidesteps the measurement problem by refusing to ask what the wave function represents physically. The collapse is not a physical process that needs to be explained. It is simply the update we make to our probability assignments when we learn the result of a measurement. Many physicists found this deeply unsatisfying. Einstein found it deeply unsatisfying. To say that physics cannot describe reality, only observations, seemed to many like a retreat from what science is for. But the Copenhagen interpretation was pragmatically successful. It told physicists exactly what they needed to do to make predictions, without getting tangled in metaphysics. For most of the 20th century, many physicists adopted the attitude sometimes summarized as "shut up and calculate," use the formalism, "don't ask what it means." A second interpretation emerged in the late 1950s from a young physicist named Hugh Everett, working at Princeton. Everett proposed taking the Schrödinger equation seriously at all times, without any special collapse postulate. The wave function, in his view, always evolves according to the Schrödinger equation, continuously and deterministically, without ever collapsing. But then what happens when a measurement is made, and a definite outcome is observed? Everett's answer was radical. All outcomes occur. When a quantum system in superposition interacts with a measuring device, the device also enters a superposition. It becomes entangled with the system it is measuring. A version of the device records outcome A, and a version records outcome B. The universe branches. Both versions continue to evolve in separate, non-interacting branches of a vast quantum multiverse. Each version of the observer sees a definite outcome, but the outcomes differ between branches. This is the many worlds interpretation. It requires no collapse, no special role for measurement or observation, no deviation from the Schrödinger equation. It is mathematically elegant. It takes quantum mechanics completely seriously, without any modifications or additions. The cost is ontological extravagance on a staggering scale. Every quantum event, every radioactive decay, every photon that either passes through or reflects off a glass surface, every electron that goes through one slit or the other, branches the universe into multiple copies. The number of branches is not merely large, it is, in any meaningful sense, infinite and growing at every moment, at every point in space. Many physicists who have thought carefully about the many worlds interpretation consider it the most intellectually honest response to quantum mechanics. Some find it deeply appealing precisely because of its austere commitment to taking the mathematics seriously. Others find the proliferation of unobservable universes too high a price to pay. There are other interpretations as well. The pilot wave theory, developed by Louis de Broglie and later extended by David Bohm, proposes that particles have definite positions at all times, guided by a real wave that evolves according to the Schrödinger equation. This theory is deterministic and realist. It restores the picture of a world with definite properties independent of measurement. But it achieves this at the cost of making the guiding wave non-local in a very explicit and uncomfortable way. Relational quantum mechanics, developed by Carlo Rovelli in the 1990s, proposes that quantum states are not absolute but relative, defined only in relation to a particular observer or system. The wave function of a system is not a property of the system alone, but of the relationship between the system and whatever is interacting with it. Different observers can have different mutually consistent descriptions of the same system without any contradiction. Quantum Bayesianism, or QBism, goes further still, treating the wave function as an agent's personal probability assignment, a description of their beliefs and expectations, not of anything in the external world. In this view, the collapse is not a physical process at all. It is simply the update of a rational agent's beliefs in response to new information. Each of these interpretations resolves the measurement problem in a different way. Each has philosophical costs and philosophical benefits, and none of them can currently be distinguished from the others by any experiment, because they all make the same predictions about the outcomes of measurements. The question of what quantum mechanics means, of what it is actually telling us about the nature of reality, remains open. A century into the quantum era, we still do not know what we are talking about. Decoherence deserves particular attention because it has clarified something important about the relationship between the quantum and classical worlds, even if it has not resolved the deeper interpretational questions. When a quantum system interacts with its environment, with the air molecules around it, the photons passing through it, the electromagnetic fields fluctuating in its vicinity, it becomes entangled with an enormous number of degrees of freedom. The wave function of the system becomes correlated with the wave function of the environment in a way that causes the quantum superpositions to become effectively invisible. Consider an electron in a superposition of two states. If the electron interacts with even a single photon, the photon's state becomes correlated with the electron's state. The total quantum state, electron plus photon, is now entangled. The superposition is still there in the combined wave function. But the two branches of the superposition, the branch where the electron is in state A and the branch where it is in state B, are now correlated with different states of the photon. And as the photon goes on to interact with other things, and those things interact with other things, the entanglement spreads rapidly through the environment. The result is that the two branches become orthogonal. They no longer interfere with each other. The quantum coherence that made the superposition a genuine quantum superposition, capable of producing interference effects, has leaked out into the environment and become distributed across so many degrees of freedom that it is practically impossible to recover. The system now behaves, for all practical purposes, as if it has a definite classical state. This process, decoherence, happens extraordinarily rapidly for any macroscopic object. An object the size of a grain of sand in ordinary air decoheres in times measured in fractions of a nanosecond. An object the size of a human body decoheres in times so short they cannot be meaningfully expressed in ordinary units. This is why we never observe macroscopic objects in quantum superpositions. It is not that quantum mechanics does not apply to them, it does. It is that their quantum coherence is destroyed by their interaction with the environment before any superposition can become apparent. Decoherence explains why the classical world emerges from the quantum world. It explains why large objects have definite positions, why measurement results are unique and irreversible, why we never see a cat that is both alive and dead. These are not features added to quantum mechanics by hand. They emerge naturally from the Schrödinger equation when you take the environment into account. But decoherence does not resolve the measurement problem. It explains why different branches of the wave function stop interfering with each other. It does not explain why only one branch is experienced. In the language of the many worlds interpretation, decoherence explains why the branches separate, but all branches are still there. In any interpretation that requires collapse to a single outcome, decoherence explains why the collapse appears to happen at a certain scale, but does not explain what the collapse actually is. The emergence of the classical from the quantum is partially understood. The deeper question of what happens to the branches not experienced remains. Now we turn to the very largest question that quantum mechanics touches, the one that connects the quantum world to the structure of the universe as a whole. What happened at the beginning? The universe, according to the best current understanding, began approximately 13.8 billion years ago in a state of extraordinary compression and heat. All the matter and energy that now fills the observable universe, all the hundreds of billions of galaxies, each containing hundreds of billions of stars, was compressed into a volume unimaginably smaller than the period at the end of this sentence. The temperature was not merely high. It was so high that the very concepts of temperature and energy and matter as we understand them break down. This is what we call the Big Bang. And at the moment of the Big Bang, or rather, in the earliest moments after it, before the universe had expanded and cooled enough for the laws of physics as we know them to apply, quantum mechanics was not merely one consideration among many, it was everything. In that first unimaginable instant, the entire universe was a quantum system, a single wave function encompassing all of space and all of time. The distinction between observer and observed, which already causes such philosophical difficulty in ordinary quantum mechanics, becomes even more fraught when the system being described is the universe itself. There is nothing outside the universe to observe it. There is no external measuring device. There is no vantage point from which to apply the standard rules of quantum mechanics, because those rules assume a separation between the system being described and the apparatus doing the describing. The application of quantum mechanics to the universe as a whole, cosmological quantum mechanics, requires a version of the theory that does not rely on any such external observer. Several approaches have been proposed. The most influential is the Wheeler-DeWitt equation, developed in the late 1960s by John Archibald Wheeler and Bryce DeWitt. It is a version of the Schrödinger equation applied to the geometry of space itself, to the wave function of the universe. The Wheeler-DeWitt equation has a remarkable property. It contains no explicit time variable. The wave function of the universe does not evolve in time in the way that an ordinary quantum system does. Time in this framework is not a background against which the universe evolves. Time is something that emerges from the internal relationships within the universe, from the correlations between its parts. This is a deeply strange idea. We experience time as the most fundamental feature of our existence. It is the medium through which everything happens. The suggestion that time is not fundamental, that it is emergent, that it arises from something timeless, is difficult to absorb. And yet it is one of the most serious proposals in quantum cosmology, and it has significant mathematical support. The philosopher of physics Julian Barbour has developed this idea at length, arguing that what we call time is a sequence of configurations, of momentary states of the universe, and that our experience of time flowing is a consequence of the way these configurations are ordered by their internal complexity, not of any underlying temporal flow. The universe, in this view, is a vast collection of nows, arranged by their relationships to each other. The experience of moving through time is, in a sense, an illusion. a consequence of the correlations between the memories encoded in our current configuration and the configurations we think of as the past. Whether this picture is correct, or whether time is truly fundamental in a way that resists this kind of reduction, remains entirely open. But it illustrates the depth of the conceptual challenges that arise when quantum mechanics is applied to the universe as a whole. There is another approach to quantum cosmology that deserves attention because it addresses one of the deepest questions of all. Why is there something rather than nothing? In 1982, the physicist Alexander Vilenkin proposed that the universe could have arisen from literally nothing through a process of quantum tunneling. The argument goes like this. Quantum tunneling allows particles to pass through energy barriers they classically could not surmount. The vacuum, empty space, is a quantum system with a ground state energy. It is possible, in principle, for a universe to tunnel from a state of nothing, no space, no time, no matter, into a state of something. The probability of this happening in any given moment is extraordinarily small, but if the concept of a moment has any meaning in a state of nothing, it will happen eventually. This proposal, the universe as a quantum tunneling event, is not universally accepted. There are serious objections to it, including the difficulty of defining what nothing means precisely enough to apply quantum mechanics to it. The concept of nothing that Vilenkin uses is not truly nothing. It is a mathematical structure, a kind of quantum geometry with particular properties. Whether this is the same as nothing in any philosophically meaningful sense is questionable. But the proposal captures something important. The universe is a quantum system. Its origin, if it had one in the ordinary sense, may be a quantum event. The laws of quantum mechanics, which govern the behavior of the smallest things, may also govern the existence of the largest thing of all. In 1983, Stephen Hawking and James Hartle proposed a different approach, called the no-boundary proposal. In their picture, the universe has no beginning in time. Instead, when you trace the history of the universe backward, when you ask what was happening before the Big Bang, you find that the concept of before becomes meaningless in the same way that asking what is south of the South Pole becomes meaningless. Time, in the earliest moments of the universe, is not like time as we experience it. It has a spatial character. There is no earliest moment, just as there is no southernmost point on the surface of a sphere. The universe simply is, with no edge and no boundary in time. This is a mathematically precise proposal, and it makes specific predictions about the properties of the cosmic microwave background, the faint radiation that fills the universe and carries information about its earliest epochs. Whether those predictions match what is observed is a matter of ongoing debate. What is certain is that the origin of the universe is a quantum mechanical question. Whatever happened at the beginning, whether it was a tunneling event or a no-boundary origin, or something else entirely that we have not yet imagined, it was governed by quantum mechanics. The universe began quantum. It is, at its deepest level, still quantum. And the quantum world is not something we study from the outside. It is the inside of everything. The great missing piece in all of this is gravity. Quantum mechanics describes three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, with extraordinary precision within the framework of quantum field theory. The Standard Model unifies these three forces into a single mathematical structure. It has been tested to extraordinary precision and has never been found to be wrong. But gravity is not part of the Standard Model. Gravity is described by Einstein's general theory of relativity, which treats space-time as a smooth, continuous, dynamical entity that curves in response to the presence of mass and energy. General relativity is not a quantum theory. It does not quantize space-time into discrete units. It does not describe gravity as mediated by quantum particles. It is a classical theory in the technical sense. It describes continuous fields and continuous geometry. For most practical purposes, this does not matter. The scales at which quantum gravitational effects would be significant, the Planck scale, where both quantum uncertainty and gravitational curvature become important simultaneously, are so small that no experiment ever conducted has come close to probing them. The Planck length is approximately 1.6 times 10 to the power of -35 meters. The smallest scales currently accessible to experiment, those probed by the Large Hadron Collider, are roughly 20 orders of magnitude larger than the Planck length. The gap between what we can measure and what we need to understand is enormous. But the gap matters. In certain extreme physical situations, both quantum mechanics and gravity are simultaneously important. Inside black holes, where matter is compressed to a singularity, the space-time curvature becomes infinite and the energy densities become quantum relevant simultaneously. In the very first moments of the Big Bang, when the universe was smaller than the Planck length, quantum gravity was everything. Without a theory of quantum gravity, we cannot describe these situations. We cannot understand the true nature of black holes. We cannot understand the origin of the universe. The search for a theory of quantum gravity is the deepest unsolved problem in fundamental physics. String theory is the most developed attempt to solve it. The basic idea of string theory is to replace the point-like particles of the Standard Model with one-dimensional objects, strings, vibrating in a higher dimensional space. Different vibrational modes of a string correspond to different particles, just as different vibrational modes of a guitar string correspond to different notes. The graviton, the hypothetical quantum particle that would carry gravity, emerges naturally as one of the vibrational modes of the string. String theory was developed intensively in the 1980s and 1990s and attracted enormous talent and resources. It has remarkable mathematical properties. It is consistent. It does not produce the infinities that arise when you try to combine ordinary quantum mechanics with general relativity. It unifies all the known forces and particles within a single framework. It has led to deep and beautiful mathematical discoveries. But it has also faced serious challenges. The most fundamental is that string theory does not make unique predictions. The equations of string theory have an enormous number of solutions. Estimates range into the tens of hundreds of power, each corresponding to a different universe with different physical laws. Our universe is one of these solutions, but string theory provides no mechanism for selecting which solution is realized. This is called the landscape problem, and it has led some physicists to embrace the idea of a multiverse, the idea that all solutions are realized in different regions of an eternally inflating universe, and others to conclude that string theory, for all its mathematical beauty, is not a scientific theory in the ordinary sense, because it does not make falsifiable predictions. Loop quantum gravity is a different approach. Rather than starting with strings and extra dimensions, loop quantum gravity starts with the mathematics of general relativity and attempts to quantize it directly. The result is a picture in which space itself is discrete, made of finite indivisible units called spin networks, whose links represent quantum states of the gravitational field. The geometry of space is not smooth but granular at the Planck scale, like a fabric woven from discrete threads. Loop quantum gravity makes predictions about the very early universe. Specifically, it predicts that the Big Bang singularity is replaced by a quantum bounce, in which a previous collapsing universe reached a minimum size determined by quantum gravity and then rebounded into expansion. If this is correct, our universe did not begin at the Big Bang. The Big Bang was a bounce. There was a universe before it, perhaps many universes, bouncing and expanding in an eternal cycle. Whether loop quantum gravity is correct is not yet known. It makes predictions that are, in principle, testable through observations of the cosmic microwave background and the gravitational wave background, but the signals are at or below the current limit of detection. Both string theory and loop quantum gravity, and several other approaches besides, remain works in progress. The theory of quantum gravity has not been found. It may require not just new mathematics, but new concepts, ways of thinking about space and time and matter that have not yet been invented. There is one more thing the quantum world touches that we have not yet mentioned. One more domain where quantum mechanics raises questions that go to the very deepest level of what we are: consciousness. The connection between quantum mechanics and consciousness is one of the most controversial topics in science. Most physicists are skeptical of attempts to link them. They worry that the connection is motivated more by the desire to find a scientific basis for the mystery of consciousness than by any genuine theoretical necessity. And there are good reasons for skepticism. Quantum coherence is destroyed by decoherence extraordinarily rapidly in warm, wet biological systems. The brain operates at temperatures and scales where quantum effects seem unlikely to play any significant computational role. And yet the question will not entirely go away. The measurement problem, the question of what constitutes a measurement, of what collapses the wave function, has led some physicists and philosophers to take seriously the possibility that consciousness plays a special role in quantum mechanics. The physicist Eugene Wigner, one of the pioneers of quantum mechanics, argued that the chain of physical interactions that constitutes a measurement can only be terminated by a conscious observer. The wave function of the observed system becomes correlated with the wave function of the measuring device, which becomes correlated with the wave function of the observer's sense organs, which becomes correlated with the wave function of the observer's brain. And at some point, a conscious experience occurs, and a definite result is obtained. Wigner later moved away from this position. Most physicists reject it. The idea that consciousness is the special ingredient that collapses wave functions faces the problem of explaining what counts as a conscious system and why the universe managed to evolve at all before consciousness existed. The physicist Roger Penrose has proposed a different connection. He argues that the problem of consciousness, specifically the way human mathematical understanding, seems to go beyond what any fixed computational algorithm could achieve, points to a non-computational process at the heart of cognition. And he suggests that this non-computational process is related to quantum gravity. Specifically, he proposes that quantum superpositions in the brain are resolved not by ordinary decoherence, but by a quantum gravitational effect. A collapse driven by the instability of superpositions involving different space-time geometries. This process, which he calls objective reduction, would be genuinely non-computational and might underlie conscious experience. The biologist Stuart Hameroff, working with Penrose, proposed that the relevant quantum processes take place in microtubules, protein structures inside neurons. The Penrose-Hameroff hypothesis remains highly speculative and is rejected by most neuroscientists and most physicists. There is no experimental evidence for it, but it represents a serious attempt to connect two of the deepest mysteries, the nature of quantum mechanics and the nature of consciousness, within a single framework. What we can say, with somewhat more confidence, is this: the relationship between mind and world that quantum mechanics forces us to confront is genuinely puzzling in ways that go beyond ordinary physics. The role of observation in quantum mechanics, the fact that, in some interpretations, the outcomes of quantum events are only defined relative to observers, touches on deep questions about the relationship between consciousness and physical reality. Whether or not consciousness plays a special role in quantum mechanics has reopened questions about that relationship that were thought to have been settled. The quantum world and the conscious world are not obviously separate. What their connection is, if they have one that goes deeper than the obvious fact that brains are made of quantum matter, remains one of the great open questions. We have now descended as far as current understanding reaches. We have gone from the surface of things, from the solid, familiar surface of an ordinary object, down through the atom and the nucleus and the quarks, through the quantum fields that underlie all matter, through the entanglement and uncertainty and superposition that define the quantum world. We have asked what it all means and found that a century of effort has produced multiple incompatible answers, none of them fully satisfying. We have traced the quantum world to the origin of the universe and found that even the beginning is a quantum question. We have confronted the gap between quantum mechanics and gravity, the deepest unsolved problem in fundamental physics. We have touched on the possibility that consciousness itself is somehow entangled with the strangeness of the quantum world. At every level, we have found the same thing. The world is not what it appears to be. The apparent solidity and definiteness and separateness of things are features of a particular scale, the scale at which we live, that do not survive descent to the fundamental level. Beneath the surface, things are probabilistic and connected, and uncertain and strange in ways for which ordinary language has no adequate vocabulary. And yet, the quantum world is not a failure of reality. It is reality seen more clearly. The uncertainty and the probability and the entanglement are not imperfections in the structure of things. They are the structure of things. The universe is quantum all the way down. And a quantum universe, strange as it is one that works, that has the right constants, the right fields, the right forces to build atoms and molecules and stars and planets and cells, and eventually creatures capable of asking what the universe is made of. The universe is made of quantum fields, and quantum fields, at a low enough temperature, in the right combinations, with the right laws, produce all of this. The table, the room, the darkness, the breathing, the thoughts that are, even now, beginning to dissolve at their edges, losing their urgency, softening into something that is no longer quite thought. There is a quality to the hours just before sleep, or perhaps just after it, in that ambiguous territory between waking and dreaming, when the boundaries of things become less sharp, when the distinction between self and world, between inside and outside, between now and not now, becomes less insistent. When the mind loosens its grip on the categories it uses to organize experience and rests, briefly, in something less structured. Physicists sometimes report something similar when they spend a long time immersed in the quantum world. Not that they lose their grip on ordinary reality, they do not, and the ordinary world is waiting for them every time they look up from their equations. But there is a quality of attention that quantum mechanics cultivates, an awareness of the strangeness beneath the familiar, an understanding that the categories of ordinary experience, solid, liquid, gas, here, there, before, after, particle, wave, are not the fundamental categories of the universe. They are useful approximations, valid at particular scales, that dissolve when you look closely enough. To know this, to really know it, not just as an abstract fact, but as something you have followed step by step, changes the way the ordinary world looks, not dramatically, not in any way that interferes with the practical business of living, but somewhere in the background of experience there is a different depth to things. The table is still there, solid and reliable and ordinary, but you know what it is made of now. You know about the empty atom and the quantum electron and the flickering vacuum. You know that the solidity is a force field, and the force field is a quantum field, and the quantum field pervades all of space. The ordinary world and the quantum world are not two separate places. They are the same place at different scales. And you live in both of them simultaneously, always, whether you are aware of it or not. Your body is quantum mechanical, not in some metaphorical sense, in the literal, technical sense that every atom in it is a quantum system, that the chemistry sustaining every cell is governed by quantum mechanics, that the electrons moving through the neurons of your brain are quantum objects obeying quantum rules. The experience you are having right now, this particular texture of awareness, this fading boundary between thinking and not thinking, is the product of quantum processes happening at scales 1 billion times smaller than anything you can see. What those processes add up to, and how they add up to it, remains the deepest mystery. We do not know how consciousness arises from matter. We do not know whether the quantum world plays any special role in that arising. We do not know whether the question even has an answer in the terms we currently have. But we know this: whatever you are, whatever the experience of being this particular pattern of matter, in this particular moment, in this particular room, it is made of quantum fields. It is an excitation of the universe, a local, temporary, astonishing increase in complexity that will persist for a time and then dissolve back into the fields from which it came. And while it persists, it can look up. It can ask what it is made of. It can follow the question down through layer after layer of reality, from the surface to the atom, to the nucleus, to the quark to the field, and find at every level something more surprising than what came before. It can stand at the edge of what is known and look out over the territory that is not yet understood. The theory of quantum gravity that does not yet exist. The explanation of why these particular quantum fields with these particular constants, the connection between the quantum world and the world of experience. And feel not frustration at what is missing, but something closer to wonder at how much has been found. The universe is 13.5 billion years old. It has been quantum all that time, and no one knew it until a little more than a century ago. A century of quantum mechanics has built the technology that fills modern life, probed the interior of the proton, detected the Higgs boson, entangled particles across rooms and then across cities, created Bose-Einstein condensates, built the first quantum computers. A century has brought us to the edge of the deepest questions. What the next century brings, no one can say. The theory of quantum gravity may be found. The measurement problem may be resolved. The connection between quantum mechanics and consciousness may be clarified. Or, entirely new questions may emerge that we cannot currently imagine, as the quantum questions of the 20th century could not have been imagined by the physicists of the 19th. The universe is not finished being strange. The darkness in the room is the same darkness it has been for hours. Nothing has changed. The quantum fields are where they were. The virtual particles are flickering. The electrons are in their clouds. You have been on a long journey, and you are back where you started. In a body, in a room, in the ordinary world of solid surfaces and consistent light and reliable cause and effect. But you know now what the ordinary world is built from. You know the quantum ground beneath the classical surface. You know that the certainty of things is borrowed from an underlying uncertainty, that the solidity is borrowed from an underlying emptiness, that the definiteness is borrowed from an underlying superposition that decohered too fast to be seen. Let that knowledge rest in you now. You do not need to hold it. You do not need to think about it. It is simply there, settled into the background of whatever awareness remains. The quantum world does not require your attention to do its work. It was doing its work before you were born. It will do its work long after every thought you have ever had has dissolved back into the fields from which it came. The electrons are in their clouds. The vacuum is alive with its flickering. The fields extend in every direction, through the walls, through the earth, through the sky, out to the edges of the observable universe, and presumably far beyond. You are part of it. Not metaphorically, not poetically, literally, physically, quantum mechanically part of it, made of the same fields, sustained by the same forces, uncertain in the same way, connected through the entanglements of a universe that has been mixing and interacting for 13.5 billion years to everything that has ever existed. There is nothing separate. There is only the quantum world, and you are in it, and it is in you, and the boundary between inside and outside is, at the fundamental level, not quite where it appears to be. Let your breathing slow. Let the thoughts continue their dissolving. The quantum fields will take care of the rest.